right. Oh boy. Here we go again. Here we go again. Here we go again. Bum. Alright, should be good. Should be good. Should be good. Bleep. Chat here. Chat. I think we're good to go here. Alright, let's try it. Should be alright. Better not be dead. Alrighty! Dun 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 dun. Welcome back. Welcome back. I appreciate you guys being here and hanging out with me. Sorry for the cringe intro. Just hyped to be here, you know, as all you guys are. Yeah, I hope you guys are all having a good time.
Harry says hello, Michael.
Mr. Harry! Let me go ahead and let's get some opening tunes here. All right, Mr. Harry, thank you for being here, being that first person up on YouTube. Thanks so much for coming in. All right, you guys. Cool. Let's wait for some people to roll on in here, and we'll get this going here. If you guys are here, part of the early crew, leave a like. If you guys are in the Discord, give say Discord in chat, so I know you guys are a part of the Discord crew as well. Let's go. We are live watching MIT 6.0002 lecture 6. Moving quick, boys. Y'all. All right. Let's just go ahead and get into this, yeah? Let's go ahead and just jump on him. Okay. Okay, so I'll start recording here for the MIT. We're keeping going here with the theme. All right. Ready? I'll start here. All right. Okay, we are back once again. Today is Monday, August 4th, 2025, and we're going to be jumping back into MIT OpenCourseWare 6.0002 Fall 2016, Introduction to Computational Thinking and Data Science, Lecture 6, Monte Carlo Simulation by instructor John Gutzag. Mr. John is back, giving us a lecture on a Monte Carlo simulation in Roulette. So I think this is going to take a lot of the information from the last lecture about kind of setting up simulations with some simple dice roll examples, and now kind of actually using some simulations to maybe some real world applications here. So let's go ahead and dive into today's lecture and let's get going here. We're almost halfway done with the course, so in terms of lecture content, so that's pretty awesome. Let's keep going here. If you guys are on YouTube, or if you guys are following along, this is the recorded watch-along series that I am uploading back to my channel. You can catch this live as I watch and stream these lectures live and learn computer science and Python and programming live every single day after my 9-to-5 job as a chemist. So thank you guys so much for being here, and make sure you join us live in the next one. All right, let's go ahead and get going here.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT.
All right, here we go. Here we go. Let's cook, boys.
Welcome to Lecture 6.
Woo!
As usual, I want to start by posting
John.
some relevant reading.
John.
For those of you who don't know, this lovely picture is of the casino at Monte Carlo. And shortly you'll see why we're talking about casinos and gambling today.
Ooh, this will be
Not
fun.
because I want to encourage you to gamble your life savings away. A little history about Monte Carlo simulation, which is the topic of today's lecture.
Okay.
The concept was invented by the Polish-American mathematician Stanislaw Ulam, probably more well known for his work on thermonuclear
Marty
weapons
says, "Hey, Mike."
than on mathematics.
Hey, Marty.
But he did do a lot of very important mathematics earlier in his life. The story here starts that he was ill, recovering from some serious illness, and was home and was bored.
Playing a lot
and
of
was
solitaire.
playing a lot of games of solitaire,
Okay.
a game I suspect you've all played. Being a mathematician, he naturally wondered, what's the probability of my winning this stupid game, which I keep losing?
Yeah.
And so he actually spent quite a lot of time trying to work out the combinatorics so that he could actually compute the probability. And despite being a really amazing mathematician, he failed. The combinatorics were just too complicated. So he thought, well, suppose I just play lots of hands, count the number I win, divide by the number of hands I played. And then he thought about it and said, well, I've already played a lot of hands and I haven't won yet. So it probably will take me years to play enough hands to actually get a good estimate, and I don't want to do that. So he said, well, suppose instead of playing the game, I just simulate the game on a computer.
Okay.
He had no idea how to use a computer, but he had friends in high places.
Okay.
And actually talked to John von Neumann, who is often viewed as the inventor of the stored program computer, and said, John, could you do this on your fancy new ENIAC machine? And on the lower right here, you'll see a picture of the ENIAC.
That's kind of
It
nuts.
was a very large machine. It filled a room. And von Neumann said, sure, we could probably do it in only a few hours of computation.
It's a giant bit board.
Today, we would think of a few microseconds, but those machines were slow. Hence was born Monte Carlo simulation. And then they actually used it in the design of the hydrogen bomb. So it turned out to be not just
All right, here
useful
we go.
for
This is going to be a fun one.
cards. So what is Monte Carlo simulation?
Okay.
It's a method of estimating the values of an unknown quantity using what is called inferential statistics. And we've been using inferential statistics for the last several lectures. The key concepts, and I want to be careful about these because we'll be coming back to them, are the population. So think of the population as the
So I want to make sure I'm following along here. I don't want to fall behind. So let's just get this real quickly. So the Monte Carlo simulation, right, is a method of estimating the value of unknown quantity, right? A method of estimating the value of an unknown quantity using the principles of inferential statistics, right? And we know that inferential statistics, right, are population, a set of examples, and then you have a sample, which is a proper subset of a population. And you have a key fact, which is a random sample, tends to exhibit the same properties as the population from which it is drawn, right? So you have a population, like a set of examples. So think of like a city of people, right? And then you have like a little area, a subset of a city. Like, let's take the south side of the city, and let's say they all kind of have like a little slight like accent, right? There's a key fact, maybe like this random sample tends to exhibit the same properties, So, you would have like a key fact, like maybe they all have like an accent, or they all have maybe certain, maybe a height, relative height of the area or something for all the people or something. Okay, that makes sense. So then this is exactly what we did with random walks. We did with random walks in lecture 5. Okay, let's keep on pushing.
Universe of possible examples. So in the case of solitaire, it's a universe of all possible games of solitaire that you could possibly play. I have no idea how big that is, but it's really big.
Yeah.
Then we take that universe, that population, and we sample it by drawing a proper subset. Proper means not the whole thing. Usually more than one sample to be useful, certainly more than 0. And then we make an inference about the population based upon some set of statistics we do on the sample. So the population is typically a very large set of examples, and the sample is a smaller set of examples. And the key fact that makes them work
on the small set,
is that if we choose the sample at random,
I learned about that before.
The sample will tend to exhibit the same properties as the population from which it is drawn. And that's exactly what we did with the random walk.
Accents and cities, right?
Right? There were a very large number of different random walks you could take of, say, 10,000 steps.
The higher likelihood you have.
We didn't look at all possible random walks of 10,000 steps. We drew a small sample of, say, 100 such walks, computed the mean of those 100, and said, we think that's probably a good expectation of what the mean would be of all the possible walks of 10,000 steps. All right, so we were depending upon this principle. And of course, the key fact here is that the sample has to be random. If you start drawing the sample and it's not random, then there's no reason to expect it to have the same properties as that of the population. And we'll go on throughout the term and talk about the various ways you can get fooled and think you have a random sample when exactly you don't.
Okay.
All right, let's look at a very simple example. People like to use flipping coins because coins are easy. So let's assume we have some coin. All right, so I brought 2 coins, slightly larger than the usual coin. And I can flip it once, and let's consider one flip, and let's assume it came out heads. I have to say the coin I flipped is not actually a $20 gold piece.
Infinite number of times.
In case any of you were thinking of stealing it. All right.
Right.
So we got one
50,
flip.
50. We know this kind of a normal distribution.
And it came up heads, and now I can ask you the question, if I were to flip the same coin an infinite number of times, how confident would you be about answering that all infinite flips would be heads? Or even if I were to flip it once more, how confident would you be that the next flip would be heads? And the answer is not very. Well, suppose I flipped the coin twice, and both times it came up heads. And now I asked you the same question. Do you think that the next flip is likely to be heads?
It doesn't matter. It's 50-50 each time. It's independent of each
Maybe you would
trial.
be more inclined to say yes than having only seen one flip.
There is no influence.
But you wouldn't really jump to say sure. On the other hand, if I flipped it 100 times, and all 100 flips came up heads.
Each trial is independent of the previous.
Well, you might be suspicious that my coin only has a head on both sides, for example.
Oh, in this case, yeah.
Or is weighted in some funny way that it mostly comes up heads.
If you have
And
all
so
heads, 100
a lot of
flips
people,
in a row,
maybe
it's a
even
little
me,
bit sus.
if you said I flipped it 100 times and it came up heads, what do you think the next one will be? My best guess would be probably heads. How about this one? So here I've simulated 100 flips, and we have 50 heads here, 2 heads here, and 48 tails.
It's about 50-50, which is about what you would normally
And now
expect.
if I said, do you think that the probability of the next flip coming up heads is at 52 out of 100?
Well, you flipped 50 heads in a row,
Well,
48 tails in a row.
if-
Now you're flipping
if you
heads in a
had
row,
to
so you're
guess-
switching coins.
That should be the guess you make. Based upon the available evidence, that's the best guess you should probably make. Because you have no reason to believe it's a fair coin. Could well be weighted. You know, if we don't see it with coins, but we see weighted dice all the time. Or we shouldn't, but they exist. You can buy them on the internet.
This guy is such a grandpa, man. I love it.
Typically, our best
buy it
guess
on the internet.
is what we've seen. But we really shouldn't have very much confidence in that guess. Because, well, could have just been an accident. Highly unlikely, even if the coin is fair, that you'd get 50-50, right? So why, when we see 100 samples and they all come up heads, do we feel better about guessing heads for the 101st than we did when we saw 2 samples? And why don't we feel so good about guessing 52 out of 100 when we've seen 100 flips that came out 52 and 48? And the answer is something called variance. When I had all heads, there was no variability in my answer. I got the same answer all the time. And so there was no variability, and that intuitively and, in fact, mathematically should make us feel confident that, okay, maybe that's really the way the world is. On the other hand, when almost half are heads and almost half are tails, there's a lot of variance. Right? Hard to predict what the next one will be. And so we should have very little confidence that it isn't an accident that it happened to be 52-48 in one direction. So as the variance grows, we need larger samples to have the same amount of confidence.
I like that.
All right, let's look at that with a detailed example. We'll look at roulette.
Roulette, here we go. Roll them up, boys, roll them up.
The theme of Monte Carlo simulation.
Give me red,
This
give me red.
is a
Give me
roulette
black.
wheel that could well be at Monte Carlo. There's no need to simulate roulette, by the way.
Which
it's
one
a
of you guys
very
are
simple
roulette
game.
junkies?
But as we've seen with our earlier examples, it's nice when we're learning about simulations to simulate things where we actually can know what the actual answer is so that we can then understand our simulation better. For those of you who don't know how roulette is played, is there anyone here who doesn't know how roulette is played? Good for you. You grew up virtuous. All right. So, well, all right. Maybe I won't go there. All right. So you have a wheel that spins
Fair
around,
roulette.
and in the middle are a
Number
bunch of pockets.
And then you have
Each pocket has a
37,
number and a
36
color.
pockets, 1 to 36.
You bet in advance on what number you think is going to come up or what
You have a
color
ball,
you think is going to
you
come
have
up.
pockets.
Then somebody
You
drops a
choose a
ball in
random
that wheel,
choice
gives it a
based off the
spin.
pockets.
And through centrifugal force, the ball stays on the outside for a while, but as the wheel slows down, it heads towards the middle, and eventually it settles in one of those pockets, and you win or you lose. Now, you can bet on it, and so let's look at an example of that. So here's a roulette game. I've called it fair roulette because it's set up in such a way that, in principle, if you bet, your expected value should be 0. You'll win some, you'll lose some, but it's fair in the sense that it's not either a negative or a positive sum game. So, as always, we have an underbar init. Typically, well, we're setting up the wheel with 36 pockets on it. So you can bet on the numbers 1 through 36.
So pocket odds is the length.
That's the way
-1.
range works, you'll recall. Initially, we don't know where the ball is, so we'll say it's none. And here's the key thing is, if you make a bet, this tells you what your odds are. That if you bet on a pocket and you win, you get len of pockets -1. So this is why it's a fair game, right? You bet $1. If you win, you get $36, your dollar plus 35 back. If you lose, you lose.
Okay, so
All
if
right,
you hit on a
self.spin will be
pocket,
random
you
dot
get
choice
the
among
value
the pockets.
of every pocket.
And
one.
then there's simply bet, where you just can choose an amount to bet and the pocket you want to bet on. I've simplified it. I'm not allowing you to bet here on colors. All right, so now we can play it. So here's play roulette.
This is cool. We should build a casino as a project.
I've made game, the class, a parameter because later we'll look at other kinds of roulette games. You tell it how many spins, what pocket you want to bet on. For simplicity, I'm going to bet on the same pocket all the time. Pick your favorite lucky number and how much you want to bet. And then we'll have a simulation just like the ones we've already looked at. So the number you get right starts at 0. For I in range number of spins, we'll do a spin. And then tote pocket plus equal game.bet
So
pocket. It
spin.
will come back either 0 if you've lost.
You come back
or
with your total pocket
35
value.
if you've
okay.
won. And then we'll
And
just
here's
print the
your
result.
odds. Pocket with
So we
total
can do
spins,
it,
not per spin.
In fact, let's run it.
We should just build a little casino game in Python. That'd be fun for project.
So here it is. I guess I'm doing a million games here, so quite a few. Actually, I'm going to do
3
2. I'm going
times.
to look what happens when you spin it 100 times, what happens when you spin it 1,000,000 times. And we'll see what we get. So what we see here is that we do
go.
100 spins.
Oh,
The first time I did it, my expected return was minus 100%. I lost everything I bet.
dang.
Not so unlikely, given that the odds are pretty long, that you do 100 times without winning.
Got washed.
Next time I did 100, my return was a positive 44%,
Hey.
and then a positive 28%. So you can see for 100 spins, it's highly variable what the expected return is. That's one of the things that makes gambling attractive to people, right? That if you go to a casino, 100 spins would be a pretty long night at the table. And, maybe you'd won 44%. You'd feel pretty good about it. What about 1,000,000 spins? Well, people aren't interested in that, but the casino is, right?
Hey, Austin, how's it
They
going,
don't
dude?
really care what happens with
A million
100
spins sitting
They
there at
care
the
what
table.
happens with
Come
1,000,000
on.
spins.
Nine,
It
nine, nine,
happens
nine,
when
nine, nine,
everybody
nine.
comes every night to play.
Crazy.
And there what we see is, you'll notice much less variance. Happens
be
to
the
be
longest
minus
binge or night
0.04
of
plus
all time,
0.6
man.
plus 0.79. So it's still not 0, but it's certainly, these are all closer to 0 than any of these are. We know it should be 0, but it doesn't happen to be.
You have
in these
more
examples.
variance because you have 36 opportunities
But
of
not only
variance.
are they closer
right?
to 0, they're
So you
closer
need more
together.
sample sizes for
There's much
expected
less
return.
variance in the results, right? So here I show you these three numbers and ask what do you expect to happen. You have no clue, right? So I don't know. Maybe I'll win a lot. Maybe I'll lose everything. I show you these three numbers. You're going to look at it and say, well, you know, it's going to be somewhere between around 0 and maybe 1%. But you're never going to guess it's going to be radically different from that. And if I were to change this number to be even higher, it would go even closer to 0. But we won't bother.
Nice. I like that attitude.
OK, so these are these are the numbers we just looked at because I'd set the seed to be the same. So what's going on here is something called the law of large numbers, or sometimes Bernoulli's law. This is a picture of Bernoulli on this stamp. It's one of the two most important theorems in all of statistics, and we'll come to the second most important theorem in the next lecture. Here it says, in repeated independent tests with the same actual probability, the chance that the fraction of times the outcome differs from p converges to 0 as the number of trials goes to infinity. So this says if I were to spin this fair roulette wheel an infinite number of times, the return would be 0. The real true probability from the mathematics. Well, infinite is a lot, but a million is getting closer to infinite. And what this says is the closer I get to infinite, the closer it will be to the true probability. So that's why we did better with 1 million than with 100. And if I did 100 million, we'd do way better than I did with 1 million. I want to take a minute to talk about a way this law is often misunderstood. This is something called the gambler's fallacy.
So in repeated independent tests with the same actual probability, right? So each probability is the same for every spin, right? Of a particular outcome in each test, the chance that the fraction of times that outcome occurs differs from p. The chance that the fraction of times that outcome occurs differs from p converges to 0 as the number of trials goes to infinity. Let me look up chat here. Let's open up the old chat. Let's look up, let me take this guy here in my notes. Let me say, can you break this down for me? Law of large numbers in simple digestible parts. What it's saying, if you repeat an experiment many times, and each time the chance of a certain outcome is the same, right? So the chance of getting, that value in your roulette is the same, 1 of 36. As you do more and more trials, the observed frequency, how often the outcome happens, will get closer and closer to the true probability. Think of flipping a fair coin. Okay, so let's see here. I'm going to copy that here. As you do more and more trials, the observed frequency, how often the outcome happens, will get closer and closer to the true probability. Right, so this is like with the example of flipping a coin, where if you only flip it twice or 5 or 10 times, you might get, you have actually a pretty high chance, a higher chance of getting 10 heads in a row than you would getting 100 heads in a row, right? Because if you start flipping 100, 200, 500, 1,000 heads, you're going to get closer and closer to that 50-50 probability of that, normal distribution of a coin flip, right? So it's kind of interesting, right? So, the gambler's fallacy, I guess, is, if I keep going, I'm going to hit. Well, if you keep going, your likely outcome is to kind of not really hit. It's not due. The odds are the same every single time, right? But you kind of have this idea that you increase your odds with each go, but that's not the case. So that's what he's going to go into with this kind of gambler's fallacy, I think.
And all you have to do is say, let's go watch a sporting event. and you'll watch a batter strike out for the 6th consecutive time. The next time they come to the plate, the idiot announcer says, well, he struck out 6 times in a row. He's due for a hit this time. Because
I would say he's probably even less due for a hit this time because there's probably a psychological element at play with like human psyche and, at an event like that, public events and stuff.
he's usually a pretty good hitter. Well, that's nonsense. It says people somehow believe that if deviations from expected occur, they'll be evened out in the future. And we'll see something similar to this that is true, but this is not true.
Yeah.
And there's a great story about it. This is told in a book by Huff and Geis. And this truly happened in Monte Carlo with
All right, here we
Roulette.
go. Gambler's fallacy.
And you could either bet on black or red.
Where's Tim at? We need Tim here. Where's
Black
Tim?
came up 26 times in a row.
Dang.
Highly unlikely, right? 2 to the 26 is a giant number.
That's crazy.
And what happened is word got out on the casino floor that black had kept coming up way
So
too
everyone
often.
starts betting black.
And people more or less panicked to rush to the table to bet on red,
Oh, sorry, red.
saying,
yeah.
well,
It's
it
due
can't
for
keep
red.
coming up black. Surely the next one will be red. And as it happened, when the casino totaled up its winnings, it was a record night for the casino. It just, millions of francs got bet because people were sure it would have to even out.
It's due for red.
Well, if we think about it, probability of 26 consecutive reds is that. A pretty small number. But the probability of 26 consecutive reds when the previous 25 rolls were red is
one
what?
half. One half. It's just a half every single time. But to get that
No,
half
that.
every single time, ink is way harder,
No.
harder.
If you'd had 25 reds and then you spun the wheel once more, the probability of it having 26 reds is now 0.5 because these are independent events. Unless, of course, the wheel
Yes,
is
we mentioned that earlier.
rigged.
Yeah, we
And
got
it's not.
independent events. Let's go.
People have a hard time accepting this, and I know it seems funny, but I guarantee there will be some point in the next month or so when you will find yourself thinking this way, that something has to even out. I did so badly in the midterm, I will have to do better on the final.
Doesn't change up any study habit.
That was mean. I'm sorry. All right. Speaking of means, ooh. See, Professor Grimm's not the only one who can make bad jokes. There is something, it's not the gambler's fallacy, that's often confused with it, and that's called regression to the mean. This term was coined in 1885 by Francis Galton in a paper of which I've shown you a page from it here. And the basic conclusion here was what this table says is if somebody's parents are both taller than average, it's likely that the child will be smaller than the parents. Conversely, if the parents are shorter than average, it's likely that the child will be taller than average. Now, you can think about this in terms of genetics and stuff. That's not what he did. He just looked at a bunch of data. And the data actually supported this. And this led him to this notion of regression to the mean. And here's what it is, and here's the way in which it is subtly different from the gambler's fallacy. What he said here is following an extreme event, parents being unusually tall,
The
the next random event is likely to be less extreme. He didn't know much about genetics, and he kind of assumed the height of people were random.
Yeah, that's totally. I mean, it's interesting that he had data to support that, right? But I grew up with this kid. His parents were like 6. His dad was maybe 6'6", 6'7". His mom was a really tall lady too. Was 6, probably 2, 6'3", and I think they had 6 children. I think the average height is 6'7", with the 2 boys, the oldest boy being 6'11", or 6'10", and the youngest boy being 7'1", I think he's right now. And then they have a daughter. The oldest daughter, I think, is like 6'6", and then they have another daughter that's, I think, 6'2", and then another daughter that I think is kind of more of got kind of is a lot shorter. I think probably I think it's just like 6 foot or something, like 6'1" maybe. But yeah, they got some tall kids. Let me tell you, he was on my basketball team.
But we'll ignore that. Okay, but the idea
Hey, what's
is
going on
here
you?
that
What's going
it
on,
will be
Moy?
less extreme. So let's look at it in roulette. If I spin a fair roulette wheel 10 times and get 10 reds, that's an extreme event, right? There's a probability of basically 1 over 1024.
That's an extreme event that took place, yeah.
Now, the gambler's fallacy says if I were to spin it another 10 times, it would need to even out, as in I should get more blacks than you would usually get to make up for these excess reds. What regression to the mean says is different. It says it's likely that in the next 10 spins, you will get fewer than 10 reds. You will get
So if you spin a fair roulette wheel 10 times and get 100% reds, that's an extreme event. That's 1 out of 1024. Huge hit right there, right? If it is likely that in the next 10 spins, you will get fewer than 10 reds. Okay, so it's saying that you kind of have to regress back to the mean, kind of are due to kind of go back to the average of that 50-50, right? So, but the expected number is 5, right? Because it's 50-50. If you spin 10 reds, or 10 times, you're expected to get 5. This was just an extreme event that took place with a pretty low probability. You know, a low probability does not rule out the event not being able to take place. It just has a very, very low likelihood of it happening, right? But, you know, by some odd chance on that day, on that sequence of spins, it happened. And so, people often think that, okay, so now because we had an excess of spun reds, we have to kind of regress back to the mean of that 50-50, saying, okay, the next 10 spins then will have fewer than 10 reds, which is, it probably will have fewer than 10 reds. It's likely, so that is probably true, but the expected number is 5 because it still is a 50-50 shot on every independent run.
A less extreme event.
I just use
Now,
it in
doesn't have to be
Markdown.
10.
Markdown
if
file.
I'd gotten 7 reds instead
Like a
of
README
5,
is
you
for
consider
my
that
notes.
an extreme, and you would bet that the next 10 would have fewer than 7. But you wouldn't bet that it would have fewer than 5. All right? Because of this, if you now look at the average of the 20 spins, it will be closer to the mean of 50% reds than you got from the extreme first spins. So that's why it's called regression to the mean. The more samples you take, the more likely you'll get to the mean. Yes?
So roulette wheel spins are supposed to be independent.
Yes.
It seems like the second 10 should.
Pardon?
It seems like the second 10 times that you spin it,
Yeah.
like that shouldn't have anything to do with what
Has
happens.
nothing to do with the first one.
Like you said, it's likely that you'll get like fewer than 10 reds.
Right. Because
Yeah.
you have an extreme event,
You
which
have
was
you have an extreme event that took place, but there's still a probability of each independent event is 50-50. So, it makes sense to regress back to the mean because in the next 10 spins, that extreme event, it doesn't, hold true for like the future. It's still, it kind of maybe it has a little bit of note in the back of your mind, like, oh, that could happen again, but the large majority of your mind is still focused on that 50-50, expected mean, right? Or expected average. So this is true where you will likely in the next 10 spins, you will get fewer than 10 reds because, hitting 10 more reds in a row is even crazier probability, right? So, you're probably going to get fewer than 10 reds and you're probably going to get about 5.
unlikely. And now if you have another event, it's likely to be closer to the average than the extreme was to the average. Right? And it's precisely because it is independent.
He didn't really answer that
Does that
question
make sense
well.
to everybody? Yeah.
Isn't that the same as the gambler's fallacy then? By saying that, like, because this was super unlikely, the next one's super unlikely?
No, the gambler's fallacy here.
The gambler's
And it's
fallacy
a
is
good
assuming like the
question.
opposite will
Indeed,
happen.
people
Like
often do
in terms of
get
like a
these things
dramatic
confused.
change, but this is just
The
showing.
gambler's
This is just showing like a regression back to the normal, right? The gambler's fallacy is showing like, okay, because of this, crazy odd, we are meaning to hit the opposite end or whatnot. Or maybe it's also a gambler's fallacy. There could be another end of the gambler's fallacy to be like, okay, because we've hit 10 reds in a row, we could hit an 11th. Like, it's hot, right? The hot fallacy. I'm sure there is like that fallacy as well.
gambler's fallacy would say that the second
Probably more of a
10
psychological
spins
fallacy, though, right? This is really interesting. Statistics is a
expect
lot
to
more
have
fun. I wish I
fewer
would
than
have
5
gave it a lot
reds,
more
because you're
effort
trying
in
to
college.
even out the
Maybe took more
unusual number
classes.
of reds in the first spin. Right? Whereas here, we're not saying we would have fewer than 5. We're saying we'd probably have fewer than 10. That it'll be closer to the mean, not that it would be below the mean. Whereas the gambler's fallacy would say it should be below the mean to, quote, even out the first 10. Does that make sense? OK, great questions. Thank you. All right, now, you may not know this, but casinos are not in the business of being fair. And the way they don't do that is in Europe, they're not all red and black. They sneak in one green. And so now if you bet red, well, sometimes it isn't always red or black. And furthermore, there's this 0. They index from 0 rather than from 1. And so you don't get a full payoff. In American roulette, they managed to sneak in 2 greens. They have a 0 and a double 0. Tilting the odds even more in favor of the casino. So we can do that in our simulation. We'll look at European roulette as a subclass of fair roulette. I've just added this extra pocket 0. And notice I have not changed the odds.
Euro roulette.
So what you get if you get your number
class
is no
of fair
higher,
roulette,
but you're a little bit less
adds
likely
a
to get it
pocket
because we
of
snuck in that
0
0.
to the pockets.
Then American roulette's a subclass of European roulette in which I add
American adds another pocket from a subclass of European roulette to add the double 0. Cool.
All right, we can simulate those. Again, nice thing about simulations, we can play these games. So I've simulated 20 trials of 1,000 spins, 10,000 spins, 100,000, and 1,000,000. And what do we see as we look at this? Well, right away we can see that fair roulette is usually a much better bet than either of the other two. That even with only 1,000 spins, the return is negative.
So for this, if you simulate 20 trials of 1,000 spins each, a fair roulette gives you a 5% gain. European and American, you always, dang. So those two slots, they influence you pretty drastically to skew the odds against you.
More and more, as I got to 1,000,000, it starts to look much more like closer to 0. And these, we have reason to believe, at least, are much closer to your true expectation, saying that while you break even in fair roulette, you'll lose 2.7% in Europe and over 5% in Las Vegas or soon in Massachusetts. All right. We're sampling, right? That's why the results will change. And if I ran a different simulation with a different seed, I'd get different numbers. Whenever you're sampling, you can't be guaranteed to get perfect accuracy. it's always possible you get a weird sample. That's not to say that you
Okay, so there's sampling space.
won't get exactly the right answer. I might have spun the wheel twice and happened to get the exact right answer of the return. Actually, not twice, because math doesn't work out, but 35 times and gotten exactly the right answer. But that's not the point. We need to be able to differentiate between what happens to be true and what we actually know in a rigorous sense is true, or have maybe don't know it but have real good reason to believe it's true, right? So it's not just a question of faith. And that gets us to what's in some sense the fundamental question of all computational statistics, is how many samples do we need to look at before we can have real justifiable confidence in our answer? As we've just seen, not just a few minutes ago with the coins, our intuition tells us that it depends upon the variability in the underlying possibilities.
We're going to get into confidence intervals?
So let's look at that more carefully.
Like confidence intervals?
We have to look at the variation in the data. So let's look at first something called variance. So this is variance of x. Think of x as just a list of data examples, data items. And the variance is we first compute the average of value. That's mu. So mu is for the mean.
Standard deviation is simply the square root of the variance.
For each little x and big X, we compare the difference of that and the mean. How far is it from the mean?
And square it divided by the absolute value
and square the difference, and then we just sum them. So this takes how far is everything from the mean. We just add them all up. And then we end up dividing by the size of the set, the number of examples. Why do we have to do this division? Well, because we don't want to say something has high variance just because it has many members, right? So this sort of normalizes by the number of members, and this just sums how different the members
kind of like
are from the mean.
An average, but against the
So if everything is the
distribution
same value,
the
what's the variance going to be? If I have a set of 1,000 sixes, what's the variance? Yes? 0.
Candy time.
You think this is going to be hard, but I came prepared.
He's got a slingshot.
I was hoping this would happen.
Oh my gosh. We got to watch this.
Look out. I don't know where this is going to go.
Nice, heretic dude. I got a minor in chemistry. I worked as the UTF in the chemistry department, undergraduate teaching fellow, and the laboratory instructor for the
Maybe
general
it
chemistry
isn't the best
department.
I'll go home
That's
and
awesome,
practice.
dude. Welcome in.
All right, so, and then the thing you're more familiar with is the standard deviation. And if you look what the standard deviation is, it's simply the square root of the variance. Now, let's understand this a little bit and first ask, why am I squaring this here? Especially because later on I'm just going to take the square root anyway. Well, squaring it has one virtue, which is that it means I don't care whether the difference is positive or negative, right? And I shouldn't, right? The variance, I don't care which side of the mean it's on. I just care it's not near the mean. But if that's all I wanted to do, I could take the absolute value. The other thing we see with squaring is it gives the outliers extra emphasis, because I'm squaring that distance. Now, you can think that's good or bad, but it's worth knowing it's a fact. The more important thing to think about is standard deviation all by itself is a meaningless number. You always have to think about it in the context of the mean. If I tell you the standard deviation is 100, you then say, well, and I ask you whether it's big or small, you have no idea. If the mean is 100 and the standard deviation is 100, it's pretty big. If the mean is 1 billion and the standard deviation is 100, it's pretty small. So should never want to look at just the standard deviation. All right, here's just some code to compute those. Easy enough. Why am I doing this? Because we're sort of now getting to the punchline.
Dude, I was so right.
We often
so
try and
right.
estimate values just by giving the mean. So we might report on an exam that the mean
I was
grade
so
was
right.
80.
I called that. Read that like a book.
It's better, instead of trying to describe
95%
an unknown
confident,
value by
93% confident, plus or minus.
an unknown parameter by a single value, say the expected return on betting a roulette wheel, to provide a confidence interval. So what a confidence interval is a range that's likely to contain the unknown value and a confidence that the unknown value is within that range. So I might say on a fair roulette wheel, I expect that your return will be between -1% and +1%. And I expect that to be true 95% of the time you play the game.
Yeah.
If you play 100 rolls.
You have a margin
spins.
of error with a 95%
If you take 100 spins of the
confidence.
roulette wheel, I expect that 95% of the time your return will be between this and that. So here we're saying the return on betting a pocket 10,000 times in European roulette is -3.3%. I think that was the number we just saw. And now I'm going to add to that this margin of error, which is plus or minus 3.5% with a 95% level of confidence. What does this mean? If I were to conduct an infinite number of trials of 10,000 bets each, my expected average return would indeed be minus 3.3%, and it would be between these values 95% of the time. Right? I've just subtracted and added this 3.5. Saying nothing about what would happen in the other 5% of the time. How far away I might be from this. This is totally silence on that subject. Yes?
I think you want 0.2, not 9.2.
Oh. Let's see. Yep, I do. Thank you. We'll fix it on the spot. This is why you have to come to lecture rather than just reading the slides, because I make mistakes. Thank you, Eric.
If I were to conduct an infinite number of trials with 10K bets each,
All
my
right.
expected return
So
would be
it's
3.
telling me that, and that's all it means. And it's amazing how often people don't quite know what this means. For example, when they look at a political poll and they see how many votes somebody is expected to get, and they see this confidence interval and you say, what does that really mean? Most people don't know. But it does have a very precise meaning, and this is it. How do we compute confidence intervals? Most of the time, we compute them using something called the empirical rule.
Empirical rule, okay.
Under some assumptions, which I'll get to a little bit later, the empirical rule says that if I take the data, find the mean, compute the standard deviation as we've just seen, 68% of the data will be within one standard deviation in front of or behind the mean. Within one standard deviation of the mean. 95% will be within 1.96 standard deviations. And that's what people usually use. Usually when people talk about confidence intervals, they're talking about the 95% confidence interval, and they use this 1.6 number. And 99.7% of the data will be within 3 standard deviations. So you can see if you're outside the 3rd standard deviation, you are a pretty rare bird, for better or worse, depending upon which side.
Okay, yeah.
All right. So let's apply the empirical rule to our roulette game. So I've got my 3 roulette games as before. I'm going to run a simple simulation. And the key thing to notice is really this print statement here. All right, that I'll print the mean, which I'm rounding. And then
Okay, so we have 3 different types of games here: fair roulette, European roulette, and American roulette. We're looping over each of those games and creating a results dictionary. A result which is equal to a list, right? And then we're looping through numbers of spins. And then we're going to do a game for every number of spins. Right.
And then I'm going to give the confidence intervals, plus or minus, and I'll just take the standard deviation times 1.6 times 100. Why times 100? Because I'm showing you percentages. All right? So again, very straightforward code, just simulation, just like the ones we've been looking at. And well, I don't think I'll bother running it for you in the interest of time. You can run it yourself. But here's what I got when I ran it. So when I simulated betting a pocket for 20 trials,
Hey, Tyler.
we see that of 1,000 spins each, for 1,000 spins, the expected return for fair roulette happened to be 3.68%, a bit high. But you'll notice the confidence interval, plus or minus 27, includes the actual answer, which is 0.
For 1,000 spins
And we
each.
have very large confidence intervals for the other 2 games. If we go way down to the bottom, where I've spun the wheel many more times, what we'll see is that my expected return for fair roulette is much closer to 0 than it was here. But more importantly, my confidence interval is much smaller, 0.8. So now I really have constrained it pretty well.
Yeah.
Similarly, for the other 2 games, you will see maybe it's more accurate, maybe it's less accurate, but importantly,
Yeah, that
the
makes
confidence interval is smaller. So
More-
I have
more
good
spins,
reason to
higher
believe
confidence.
that the mean I'm
Lower
computing
interval.
is close to the true mean, because my confidence interval has shrunk. So that's the really important concept here, is that we don't just compute the value in the simulation. We use, in this case, the empirical rule to tell us how much faith we should have in that value. All right. The empirical rule doesn't always work. There are a couple of assumptions. One is that the mean estimation error is 0. What is that saying? That I'm just as likely to guess high as guess low. In most experiments of this sort, most simulations, that's a very fair assumption, right? There's no reason to guess I'd be systematically off in one direction or another. It's different when you use this in a laboratory experiment, where in fact, depending upon your laboratory technique, there may be a bias in your results in one direction. So we have to assume that there's no bias in our errors. And we have to assume that the distribution of errors is normal. And we'll come back to this in just a second, but this is a normal distribution called the Gaussian.
Yeah,
Okay.
we're familiar
Under
with that.
those 2
We've
assumptions, the
implemented
empirical
Gaussian
rule
curves in our programs
will
before.
always hold.
for spectrosim.
All right, let's talk about distributions, since I just introduced one. We've been using a probability distribution. And this captures the notion of the relative frequency with which some random variable takes on different values. There are two kinds, discrete, and these when the values are drawn from a finite set of values. So when I flip these coins, there are only two possible values, head or tails. And so if we look at the distribution of heads and tails, it's pretty simple. We just list the probability of heads. We list the probability of tails. We know that those two probabilities must add up to 1. And that fully describes our distribution. Continuous random variables are a bit trickier. They're drawn from a set of reals between two numbers. For the sake of argument, let's say those two numbers are 0 and 1. Well, we can't just enumerate the probability for each number. How many real numbers are there between 0 and 1? An infinite number, right? And so I can't say for each of these infinite numbers what's the probability of it occurring. Actually, the probability is close to 0 for each of them. Is 0 if they're truly infinite. So I need to do something else. And what I do that is what's called a probability density function. This is a different kind of PDF than the one Adobe sells. So there, we don't give the probability of the random variable taking on a specific value. We give the probability of it lying somewhere between two values. And then we define a curve which shows how it works. So let's look at an example. So we'll go back to normal distributions. This is, for the continuous normal distribution, it's described by this function. And for those of you who don't know about the magic number E, this is one of many ways to define it. But I really don't care whether you remember this. I don't care whether you know what E is. I don't care if you know what this is. What we really want to say is it looks like this. In this case, the mean is 0. It doesn't have to be 0. I've shown as a mean of 0 and a standard deviation of 1. This is called the so-called standard normal distribution. But it's symmetric around the mean. Mm-hmm. And that gets back to it's equally likely that our errors are in either direction, right?
Right.
So it's peaks at the mean. The peak is always at the mean. That's the most probable value. And it's symmetric about the mean. So if we look at it, for example, and I say, what's the probability of the number being between 0 and 1? I can look at it here and say, all right, let's draw a line here and a line here. And then I can integrate the curve under here. And that tells me the probability of this random variable being between 0 and 1. If I want to know it between -1 and 1, I just do this, and then I integrate over that area. All right, so the area under the curve, in this case, defines the likelihood. Now I have to divide and normalize to actually get the answer between 0 and 1. So the question is, what fraction of the area under the curve is between -1 and 1? And that will tell me the probability.
Yeah.
So
pretty easy stuff.
What does the empirical rule tell us?
You guys have ever
What
taken like
fraction
a
is between -1
intro
and 1?
statistics
roughly?
course in college? This is pretty much what you learned about.
Yeah. 68%, right? So that tells me
This is a good
68% of the area under this curve is between -1 and 1, because my standard deviation is 1, roughly 68%. And maybe
Remember
your
back
eyes will
to this,
convince you that's a reasonable guess.
The empirical rule.
Okay, we'll come back and look at this in a bit more
Within one
detail
standard
on
deviation.
Monday of next week. and also look at the question of
One standard
why
deviation
does
to the
this
left and to
work
the right, that'd be about 68%
in
of the
so
curve.
many cases where we don't actually have a normal distribution to start with.
All right, sweet, you guys. Nice, that's awesome. Awesome, awesome, awesome. That will take us to the end of MIT Lecture 6 for MIT Open Courseware Introduction to Computational Thinking and Data Science for 2016 6.0002. Awesome lecture. That one was really fun. Kind of got a little bit slower towards the back, like 10-15 minutes there. But learning about, the different types of, applying the algorithms of, certain types of gambling or casino games like roulette and whatnot is pretty fun. So I like when these lectures, and the code lines up to some real world examples. That always helps to keep the attention span going, right? And then when you start getting in the normal curves, so anyways, you guys, that was awesome. That was a great lecture. So tomorrow we will be going and diving into the assignment for problem set 2, fastest way to get around MIT. This is the assignment that's due before the next lecture picks up. So in the syllabus here, you can see the schedule. The Monte Carlo simulation is here with problem set 2 is due here for this lecture. So we'll go ahead and take a stab at problem set 2 and get that one done, and then move on to lecture 7 and complete and then do lecture 8 and complete confidence intervals. The problem set 3, in the same sequence or whatnot. So awesome stuff there. I haven't been doing too much code on my streams as we've been doing more lecture watch alongs and kind of diving into these courses. So I need to set aside some time to do some code too. So hopefully tomorrow, after we can get through the problem set, if it's not too long, and we can do a little bit of work on our projects as well and keep going on those. I do want to start adding some more models and different types of simulations to our better options project, where we're currently, taking an options contract across some various, expirations dates. If you aren't familiar with financial quantitative like options or whatever, do a little bit of reading on them. We're taking an options contract from the options chain and running some certain models on it to assign. I think my goal is to get some like kind of weighted values to determine kind of like a model of my own, which kind of references various other indicators and models to give a weighted value to the option in terms of like a buy or not. So I think it could be a fun little experiment to kind of dive down, as we currently do options trading just for fun and whatnot. So I appreciate you guys hanging out with me here and joining me for this lecture. This was MIT 6.000 Lecture 6 Monte Carlo simulation for the Open Courseware Introduction to Computational Thinking and Data Science. All right, you guys, please leave a like and please leave a like if you guys enjoyed this one on the stream and enjoyed hanging out. Please join my Discord link down below if you'd like to get access to my entire roadmap of learning. I will be coming out with a weekly breakdown of the course, as well as providing, you can get access to my notes here and everything in there and on my GitHub as well. So let's add here, git commit. Let's do finished lecture 6. And we'll push that up. All right, you guys, thanks so much for joining me tonight, and I appreciate you guys being here. For a little bit of a slower stream today. I think people are a little bit busy today, but that's okay. I really appreciate those that were able to stop in today and hang out with me. You guys are awesome. I really honestly appreciate it, and let me know what you guys are working on and your goals in programming. I would love to make more connections on a more personal level with you guys, and kind of network and whatnot. So message me on Discord and say hello. So I'll talk to you guys later. See you guys tomorrow. Bye. Have a good one.